Welcome folks, and in today's lesson we're going to talk about thermochemical reactions. Ooh, that's a little bit of a mouthful. Thermochemical reactions. And hopefully that's going to lead to a little bit of this going on, a little bit of blowing of mind going on. And if your mind was to blow, I guess what would happen is there would be some energy absorbed or given off, in this case probably given off into the surroundings. And what we're going to talk about is how we would recognize that, how we would categorize it, how we would represent it. That's what today's lesson is going to be about. So if we think about how much energy is going to be released or absorbed, what we're essentially referring to is something called enthalpy. Enthalpy change. And this is a measure of the amount of energy released or absorbed in a reaction, in this case, your mind blowing. And I guess the amount of enthalpy involved there, the enthalpy change, would depend on a number of factors, whether it was a chemical change or a different type of change. And usually chemical changes, the enthalpy, the amount of heat involved there for a reaction, a chemical reaction, is in the range of 10 to the 2 to 10 to the 4 kilojoules for every mole. Now we're going to get to talking about this, but kilojoules usually is a measure of, or one way to measure energy. And so that is a measurement for the amount of energy per mole in a standard chemical reaction. Now, your mind could have been blown in another way. It could have been a nuclear reaction. If it was a nuclear reaction, you can expect much higher amounts of energy to be involved. And they would be in the range 10 to the 10 to 10 to the 14 kilojoules per mole. And that is why we use nuclear reactions to produce lots of heat and turn that heat into weapons and also into electricity. So let's continue. We're going to talk about thermochemical reactions in a little bit more detail. Now, just to get us started, we're going to review the first law of thermodynamics. The first law of thermodynamics, which put quite simply states that you cannot produce energy out of nothing. So in other words, the energy before is equal to the energy after. And if we just view it in terms of this seesaw or teeter-totter, that would be a balanced scenario. Another way to put it is that the total energy of the universe is constant. Now, energy, of course, hopefully you know that energy can transform from one form to another, but the total energy is constant. Now, if we look at our example here of our Earth, we're not actually looking at the universe here, rather just our little tiny, teeny portion of the universe that we call Earth. And we know that in reality on Earth, there is some energy leaving the system. If we view Earth as a system, and sometimes maybe there's energy gained by Earth. So Earth in that instance is not a closed shop. It's not the universe. So there's energy leaving and gaining. So that brings us to a conversation about systems. Okay, now there are three different systems that I want to talk about here. The three different systems are called open system, closed system, and ideal system. So we're just going to go into a little bit of detail and use some examples to talk about what those types of systems are. The first one that we're going to talk about is this notion of an open system. So if you look at the diagram shown, this is a very good example of an open system. And the reason for that is because energy is able to leave and enter this system. So energy is our red here. And when we say the system here, of course, what we're referring to in this case is this pot. And energy is allowed to go into the pot and energy is allowed to leave the pot. And it's been heated, so hopefully we can see that. Also, the other thing that's able to happen is mass, in this case, is able to enter and leave the system. So we can see that, hopefully you can see that there's some water molecules that are going to leave that system. So an open system is where energy and mass are free to come and go, enter and leave this particular system. Okay, the second type of system that we're going to talk about is a closed system. So in a closed system, we're going to do the right thing and put a little lid on top here. And when we do that, we're going to cover this system with a lid, just as we should do when we're cooking. And when we do that, we can see that some things are going to change. In terms of energy, yes, there's still going to be energy added from the heating filament, and maybe energy can leave that system. If you put your hand close to this pot here, you would see very quickly that energy would leave this system. So energy is free to come and go, if you like, into the system and out of the system. However, mass is not. So in this instance, mass is controlled and kept within the system. So that is called a closed system. So the final type of system that we're going to talk about is an ideal system. Now we're going to, in future lessons, talk about bomb calorimeters and so on, but we're just going to use a very simple example to talk about that. In an ideal system, mass and energy are not allowed to leave the system. So if we think about it, energy is not allowed to come and go in that system. There are protective sleeves in here which would hopefully trap the energy, these insulators on the outside of our thermos flask, and they would protect energy from coming and going. Heat, if you like, energy is in the form of heat in this instance. And if we look at the mass, well, there's no mass going to come or go into that system either. So these are the three different types of systems, and it's important to bear those in mind for future discussion. This brings us to a concept that's often confused, or students sometimes find confusing, and that is, how do we differentiate between heat and temperature? Because in our everyday lives, these terms are used in the same way, but they are very, very different things. Heat can be seen of almost as a verb. It involves the movement of energy, so it is the transfer of energy. It's a measure of the transfer of energy, whereas temperature is the total kinetic energy of a system. So it's the actual total kinetic energy of a system, and sometimes we use thermometers to measure that, where the thermometer rises as the molecules dance and rise a little bit more, and so we use a little device like a thermometer to measure that kinetic energy. So they are connected, and we can use a very simple equation which you may have seen before. It's a standard, very famous equation, I guess, in science to talk about this. And it is Q is equal to mc delta T. Some of you will already have seen this, where Q is a measure of the energy added or removed from the system. I'm just going to put it like this. M is obviously mass, the mass that's involved. C, we're going to get to that in a second. And delta T is a measure of the temperature difference in Kelvin or degrees Celsius. So there is a relationship between the two of those concepts. And if we look at this concept here, C is sometimes called a specific heat capacity. Now, different materials have different specific heat capacities. And it is a measure of the ability of a material to resist temperature change. specific heat capacity. So when a material has a high specific heat capacity, it means that you require a lot of energy in order to remove or to increase or decrease the temperature of that system. So specific heat capacity is the amount of energy required to increase 1 gram or 1 kilogram of a substance by 1 degrees Kelvin or Celsius. So materials like water have a very high specific heat capacity. A lot of energy is required to increase or decrease the temperature. And then other materials like metals have very low specific heat capacity. So you don't require a lot of energy to increase the temperature of a metal. Now, when we're talking about that increase in energy and so on for a system, we can talk about this in another way. We can use the term enthalpy. Now, enthalpy, put simply, is a measure of the amount of energy absorbed or released during a reaction. And under standard pressure and volume conditions, we can write that the enthalpy, denoted by delta H, is equal to plus or minus Q. So this enthalpy, if you like, is a measure of the amount of energy released or absorbed in a reaction. So if we look at our standard reaction here, we have reactants and products, obviously. And different types of reactions can be involved. So we can have a certain type of reaction where energy is consumed. So energy is consumed and taken in when products are made. Now, usually what happens there is that the products themselves will appear to be cold, and that's why I've shown this with a blue symbol. And they are that type of reaction is called an endothermic reaction. In other words, we have a gain of energy to the system. So there's a positive delta H. So the energy gained was gained by the system. We would actually feel that as being cold because the energy was actually transferred from the surroundings into the system. And so our hands will feel that as being cold. The second type of scenario is where energy is removed from the system. And of course, that would be a negative delta H. We would call this an exothermic reaction. And in an exothermic reaction, that energy is released into the surroundings. So there's two different types of reactions that we are going to talk about in this unit: endothermic and exothermic. And you should be able to reason what type of enthalpy you would be looking at for each. So there's different ways to represent these enthalpy changes, these reactions where energy is transferred in the form of heat. One of the ways is to use something called a potential energy diagram. And this is a very visual way of looking at these reactions, which makes it quite useful. And if we look at the potential energy diagrams shown, A and B, we're just going to focus on A first. Potential energy is on the y-axis, and time, if you like, the reaction progress, is on the x. And in A, we can see that the reactants have a lower potential energy than the products. And so what's actually happened here is that we see that delta H is going upwards. And we can show this as being positive, or delta H as being positive. And we already talked about the fact that A here is an endothermic reaction. In other words, the products have gained energy. So if we look at B now, we can see that the reactants appear to lose energy. In other words, the products have less potential energy than the reactants. And what we're going to see here is that this would be a negative delta H, and this is what we would call an exothermic reaction, and this would be a potential energy diagram for an exothermic reaction. this is one way to show, the energy and the enthalpy changes in a reaction. Another way would be to look at this in terms of an equation, a thermochemical equation. There, we got to it eventually. And we have our endo on the left, and we have our exo on the right. And so a good example of a endo reaction, an endothermic reaction. This one's actually caused by lightning. And lightning has such power that it can actually bring the nitrogen and oxygen gas together, and it will form nitrogen dioxide. So when we look at that reaction, we of course got to balance the reaction. And the delta H is the difference between the products and the reactions. And in this case, we can see that it's got a positive sign. And we can also see that the units here are kilojoules per mole. So in other words, there would be 66.4 kilojoules produced for every mole. And in this case, we're going to look at mole. If we take this as one nitrogen, the coefficient here would represent the number of moles. So for every nitrogen that you've got in that reaction, every mole of nitrogen, there would be 66.4 kilojoules taken into that system. Okay, so that's an endothermic reaction. An example of an exothermic reaction would be a thermite reaction, which produces huge amounts of energy. And you would probably see this in the form of a flame produced, and large amount of energies given off there. So when we look at that type of exothermic reaction, we would look at the balanced equation, which tells us that iron 3 oxide plus aluminium goes to iron and aluminium oxide. We're not going to worry about the states for now. But what we are going to worry about is that the delta H here, we'll see that there's a slight difference, a very important difference, because the delta H here is going to be a negative. And we'll see that this is a chemical reaction, so it's in that range that I talked about at the start of the video, and it's negative 850 kilojoules for every mole. Okay, so that's another way to show this, is with a thermochemical. So potential energy diagrams, thermochemical equations, where you're writing the delta H. And another way is you can actually put it into the actual equation itself. So the first equation here that we've got is water, decomposition of water into hydrogen and oxygen. You'll notice that this is an endothermic reaction, and that's shown by the fact that the energy is on the reactant side. So if you like, there was some energy gained rather than given out. So the energy was gained by the system. So this energy came in and was given to the system. The second type underneath it is an example of an exothermic reaction, where we have carbon monoxide plus hydrogen, and that's forming methanol. And we'll see that in this one, the delta H is on the reactant side, and that's for an exothermic reaction. Now we can also use this enthalpy and a concept known as molar enthalpy to figure out what is the mass of products and reactants, similarly to your stoichiometry in the past. The molar enthalpy is a definition or a term for the enthalpy of 1 mole of a substance. So a question I have here is, what is the enthalpy change when 50 gram sample of methane undergoes complete combustion according to the equation? And the equation that we've got written out. Now sometimes you might have to actually figure out this equation just when given the words. And of course you'd have to make sure that it's balanced and include the states and all of that good stuff. So we need to figure out when 50 gram sample of methane undergoes combustion. Now, you probably will need to have the molar enthalpy of combustion there, and that would probably be provided to you in a table. I certainly wouldn't expect you to memorize these things. There are table values where you have standard values for combustion of methane and other materials and gases. So the first thing that we're going to do is we're going to determine the amount of methane by using mass and molar mass. So we're going to figure out how many moles we've got. So if we look at that here, we're going to put 50 over the molar mass of methane, which is 16.05. And we're going to figure out that we actually have 3.115 moles. And then we're going to, because we already have this molar enthalpy for this combustion, we're going to figure out what is the total enthalpy change. So we're just going to take our 3.115 moles and we're going to multiply it by our negative 890.8 kilojoules per mole. Okay, we'll see that the moles are going to actually cancel here. And what we end up with is we end up with this value of 2.8 by 10 to the 3 kilojoules. So we've removed this mole, so we're getting the actual enthalpy change. And there are other things that you may be asked to figure out. For example, you can use the mole ratio to find the enthalpy of reaction per mole of oxygen, of carbon dioxide, and of water. And to do that, you just would have to understand that the mole ratios are given here. 1 is to 2 is to 1 is to 2. Okay, so that was a good introduction, hopefully, for the world of thermochemical reactions. And hopefully you're in a better spot than you were when you started the video. And if you like the video, just give it a wee thumbs up, please.